take 1 or 2 minutes time to write the problem. I hope everyone writing the problem. Some part of the question is little blur. Are you able to see that? If you are not able to read that, you can ask me. I'll tell the values or whatever. Done? Okay. I hope you have written the problem. Just go through it first. A post-tensioned beam of span length 10 meter, length of the beam is 10 meter, is pre-stressed by a parabolic cable. Profile of the cable is parabolic. Concentric at support and having an eccentricity of 250 mm at mid-span. Okay. Write the diagram for the same. Okay, it's a parabolic cable having zero eccentricity at the support and 250 mm at the mid-span. Okay. Write the diagram. Solution. Okay, write the centroidal axis. What it says is the cable is parabolic with zero eccentricity at the supports and 250 mm at the center of the span. So you write a figure of a parabolic cable now. Okay. So at support 0 and at center of the span eccentricity E is 250 mm. Okay. The cross section of high tensile wires in the cable is 500 mm square. Area of the cable is given. Just write down below as given data. Area of cable is 500 mm square. Then the wires are stressed by using a jack at left end so that the initial force in the cable at right end is 250 mm. There is jack at the left end. Let me write the figure here. Okay, there is jack at the left end. Okay, the cable is stretched by using the jack. Okay, left end so that initial force in the cable at right end is 250 kilonewton. Okay, so it is the jack is stretched or pulled in such a way that the initial force in the cable on the right end is 250 kilonewton. Okay, after jacking the cable, the initial pre-stress induced in the concrete is 250 kilonewton. Okay, the cross section area of the beam is 150 by 300, so it's having rectangular cross section. Okay, 150 by 300, 150 by 300. Cross sectional area of the section of the section is how much? 150 by 300. So you will get 45,000 mm square as area. In terms of meter square, it is 45,000 into 10 power minus 6 meter square. Okay, the area in terms of meter square is required to calculate the self weight. Correct? Huh? Then calculate the jacking force required at left end. Okay, so what is the question here? You have to calculate jacking force required at the left end so that the pre-stressing force of 250 kilonewton is induced on the right end. That is the question, first question. Okay, so first we'll solve the first question. Question A we'll solve, then we will move on to the next question. Okay, and the constants relevant for calculation of different types of losses are given. Okay, coefficient of curvature effect, wave effect, relaxation of stress. Okay, that is given as 4%. Shrinkage strain is given, creep coefficient. All the constants required to calculate different losses of stresses in the concrete are given. Okay. Now we'll solve the first question, that is jacking force at the left hand so as to cause a pre-stressing force of 250 kilonewton at the right hand. Okay, calculation of jacking force. Calculation of jacking force at left hand. Okay, jacking force at the left hand. Okay, now coefficient of curvature is given. Correct? Coefficient of curvature is given. It is given as 0.55. Write down below. Coefficient of curvature coefficient of curvature is given as, that is mu, is given as 0.55. Okay, nothing but it is frictional coefficients. Due to curvature only, there will be friction between cable and the duct. Okay, that is why it is called as coefficient of curvature. Coefficient of curvature mu is equal to 0.55. Then wave effect constant is given 0.003 per meter. Coefficient of wave effect, K is given. How much it is given? 0.003 0.003 per meter. Okay. Now, what we require? We require jacking force at the left end so as to produce a force of 250 kilonewton at the right end. This is the question. Okay. So here he has given coefficient of curvature and wave effect. Okay. So utilizing these constants, these values, you can find that the jacking force required at the left end. See, when you apply some particular magnitude of the jacking force, the full jacking force will not be transferred at the left end. Why? Because there is wave effect, there is curvature, okay, there is frictional loss that will takes place in the cable. Okay, if you apply some particular force, same force will not be transferred here. Okay, so here uh, there will be some loss due to friction. There will be some loss due to friction. If you want to produce 250 kilonewton at the right end, you need to apply some extra force so that considering the losses due to friction, 250 kilonewton will be induced at the right end. That is the question. So what we'll do, we'll utilize the formula of the frictional loss. Okay, formula of the frictional loss. So what is the formula we have? So I have opened model 4. Okay, model 2. Yes. Okay. Here we have one relation. Okay. Px is equal to P naught into e power minus mu alpha plus Ks. We will utilize this equation. This equation is given in the code book. Okay. So here. So please change the number I have written wrongly. Actually, it's not wrong. I have referred the IS 1343 2012 version. Okay. 2012 version. There in page number 25, the formula is available. But your syllabus, you have this IS 1343 1980 version. Okay, 1980 version. So in this code book at page number 33, this formula is available. Okay, Px is equal to P naught into e power minus mu alpha plus Kx formula. Okay. So we will utilize this equation here to solve the problem. We know that, right? Below. Or else from IS 1343 1980 page number 33, we have the relation P naught Px is equal to P naught into e power minus mu alpha plus Kx. Okay, write that formula. Px is equal to P naught, okay, into 1 minus mu alpha plus Kx, okay, plus Kx. Yes, mu alpha P naught into e power. Sorry. Px is equal to Px is equal to Px is equal to P naught into e power P naught into e power minus mu alpha plus Kx minus mu alpha plus Kx is the formula which is available in the code book. Okay, in the code book. So this equation can be rewritten. Okay, this equation can be rewritten as Px is equal to P naught into C e power. We have a general formula that is e power minus x is equal to 1 minus x. Okay, this is the uh, formula with respect to e power minus x. E power minus x. Okay, e power minus x is given by is equal to 1 minus x. Okay, it is a mathematical formula. Okay, so using this mathematical formula, we can rewrite this equation P naught into e power minus of mu alpha plus Kx. We can write it as 1 minus mu alpha plus Kx. In this way, we can rewrite. Okay, in this way, we can rewrite the equation so that it will be easy for us to do the further calculation. Okay. Now we'll find one by one. So what is the question here? Question here is to find P naught only. Okay, P naught only, that is jacking force required at the left end, initial force, jacking force. Okay, P naught required at the left end so as to cause a force of 250 kilonewton at the right end. Okay, now we'll find one by one. Px, Px is nothing but it is initial pre-stress at the right end. Okay, Px is equal to initial pre-stress at the right end. Okay. So initial pre-stress at the right end, pre-stressing force at the right end given. How much it is given? 250 kilonewton is given as pre-stressing force of 250 kilonewton at the right end. Okay. If you know the initial pre-stressing force at the right end, you can calculate the initial pre-stress at the right end, force by area of the cable. Okay. So you can calculate the Px now, that is initial pre-stress at the right end is equal to initial force at the initial force at right end divided by area of the cable. Area of cable. Okay. Initial force at the right end is 250 kilonewton. In terms of Newton, it is 250 into 10 power 3 divided by area of cable. How much it is given? It is given in the problem. Area of cable is given as 500 mm square. That divided by 500. Okay. So Px is equal to, please calculate the answer. Calculate the answer. Calculate the answer. And cross check your answer. Px is equal to, I got it as 500 Newton per mm square. 500 Newton per mm square. Okay, if you calculate the answer, you will get 500 Newton per mm square. If you get any other different answer, let me know, we'll correct it. Okay. Now Px is now P naught only we have to calculate initial pre-stress at the jacking end. We have to calculate. Okay, if you come to know about the initial pre-stress at the jacking end, you can calculate the initial pre-stressing force by multiplying the area of the cable. Okay, then what else is required? Mu. Mu is given in the problem. Mu is equal to 0.55. Mu is equal to 0.55. Then alpha we have to calculate. Okay, we have the guideline for calculating the alpha here in the beginning of the notes. See here, you need to refer this note for calculating the alpha. Okay, how to calculate the alpha? See, for parabolic cable and for linear cable, the calculation of the alpha formula for alpha will vary. Okay. Now initially we have to calculate slope. Okay, you need to calculate the slope, and formula for that slope will vary depending upon the cable profile, as I explained in the previous class. For parabolic cable, the slope is calculated as 4e by L, and for linear cable, slope is calculated as 2e by L. So here we have the parabolic cable in the problem. So first you calculate the slope. Slope is equal to 4e by L. Okay. Slope is equal to, yes, straight returning, right? Calculation of alpha. Okay. So for parabolic cable, alpha is equal to 4e by L. Okay, 4e by L. Okay, E is eccentricity, and 4 into E is eccentricity. Eccentricity is 250. Okay, divided by length of the beam. How much it is given? Length of the beam is given as 10 meter. Okay, length of the beam is given as 10 meter. Length of the beam is 10 meter. So here we have substituted the eccentricity in terms of mm. Here length also you substitute in terms of mm only. 10 into 10 power 3 millimeter. Okay, 10 into 10 power 3 millimeter. Okay, by this we'll get the slope. So this is slope, not alpha. Slope. Slope is equal to. Please calculate the answer. How much will get? 2 into 4 into 250 divided by 4 into 250 is 1000 divided by how much it is? 10 into 10 power 3. So you'll get 0.1 as answer. Slope is 0.1. Okay. Now you have calculated the slope, correct? For parabolic cable, formula is 4E by L. Using this 4E by L formula, first you have calculated the slope. Okay. Now coming to the calculation of alpha. Okay, that calculation of alpha depends upon the stretching condition. If the cable is pulled from one end, you need to utilize alpha is equal to 2 into slope, x is equal to L in meter. Okay, if the cable is pulled from both ends, alpha will be equal to slope and x is equal to L by 2 in meter. Okay, so here the cable is pulled from only one end, correct? Cable is pulled from only one end, so this first condition is applicable. Okay, so alpha is equal to 2 into slope and x is equal to L in meter. Therefore, as cable pulled from one end, as cable pulled from one end, alpha is calculated as 2 into slope. Okay, that is 2 into 0.1 is the slope. You will get 0.2 alpha. Okay, and what is x? X is equal to L in meter. Okay, and x is equal to length of the beam 10 meter. In meter you need to substitute. Okay, now we have calculated px, mu, alpha. Okay, k is given in the problem. Okay, k is given in the problem, and x is also we know that is 10 meter. Now you substitute everything, you will get the p naught. You will get the p naught. K is equal to 0.003. Okay, so equation, you call this as equation number 1. Therefore the equation 1 becomes, okay, therefore the equation 1 becomes px is 500 is equal to p naught into what is there next? 1 minus mu alpha plus kx. 1 minus 1 minus mu. How much it is given? Mu 0.55. Mu alpha is 0.2 plus kx. K is given as 0.003 into 10. Okay, this is very important. You need to substitute this in terms of meter only. This formula is derived such that if you substitute the x value in meter, you will get the stress in terms of Newton per mm square. Okay, so here p naught is only the unknown factor that you can solve. Please solve the answer. Let me know how much you'll get. Solve for p naught now. Please check the answer. It is 581.4 Newton per mm square. Okay. P naught is equal to 581.4 Newton per mm square. Therefore, pre-stress, okay, pre-stress at jacking end is equal to P naught is equal to 581.4 Newton per mm square. 581.4 Newton per mm square. What is the question here? Question: the jacking force required at the left end. Okay, now we got jacking stress, pre-stress at the jacking end. Okay, therefore we can calculate the jacking force. Okay, therefore jacking force is equal to, therefore the jacking force is equal to stress into area of the cable. Stress into area of cable. Okay, stress is 581.4 into area of cable is given as 500 mm square. You will get jacking force. Okay, jacking force is, if you calculate, it is 290.7 into 10 power 3 Newton. Okay, in terms of kilonewton also you can put the answer 290.7 kilonewton. So to this, the first question is over. We have solved the first question. Jacking force required at the jacking end so as to produce a pre-stressing force of 250 kilonewton at the right end, which means that if you apply a force of 290.7 kilonewton, okay, if you apply a jacking force of 290.7 kilonewton, then the pre-stressing force of 250 kilonewton will be induced on the right end. Okay, and there is some loss. That loss is due to friction or wobble effect or wave effect. Okay, due to that loss due to friction, if you apply a force of 290.7 kilonewton at the jacking end, okay, then a 250 kilonewton will be transferred at the other end of the cable. This is the meaning. Okay, I hope this is clear for everyone. Still, if you have got any doubts, you can ask students in this calculation. Okay, now moving on to the next question. The total loss of stresses in wires assuming the following data. Okay, it is also asked to find the total losses of stresses. Okay, then there will be loss due to shrinkage, there will be loss due to creep, correct? There will be loss due to relaxation of stress in steel, there will be loss due to anchorage slip. All the losses we have to calculate, and total loss we can get it by adding all the losses. Okay, so initially we have calculated now initially by this calculation you can calculate the loss due to friction, correct? Loss due to friction. How will calculate the loss due to friction? How will calculate the loss due to friction? See, stress, pre-stresses at the jacking end is 581.4 Newton per mm square. If you apply pre-stresses at the jacking end as 581.4 Newton per mm square, the final pre-stress at the right end will be 500 Newton per mm square. So there is a loss of 581.4 minus 500 due to friction. Therefore, loss due to friction is equal to, therefore, loss, or else you write the side headline as second question. Second question. Second question. Calculation of total loss. Second question B. Calculation of total loss. Okay. Now we have the data required to calculate the loss due to friction. So initial pre-stress is known. Okay. Then the final pre-stress is known. Initial pre-stress minus final stress pre-stress. Okay. Calculated with respect to loss due to friction. You can calculate. Correct. Therefore, loss, first one, loss due to friction. Loss due to friction. You can calculate. Okay, you can calculate. Initial pre-stress is just now we have calculated at the jacking end 581.4 Newton per mm square. 581.4 Newton per mm square. If you apply a stress of 581.4 on the jacking end, 500 will be transferred on the right end of the cable, minus 500. Minus 500, if you do, you will get 81.4 Newton per mm square as loss due to friction. Okay, you will get the 81.4 Newton per mm square as loss due to friction. Okay, similarly, we have to calculate all the rest of the losses. Okay, what are the other losses? Shrinkage of concrete is given. You calculate loss due to shrinkage, loss due to shrinkage, loss due to shrinkage. So he has given a shrinkage coefficient, correct? Shrinkage of concrete is given as 0.0002. Shrinkage of concrete is given, correct? Shrinkage of concrete is equal to epsilon CS. It is given as 0.0002. Okay. Then we have the formula to calculate the loss due to shrinkage. Just go through it. Loss due to shrinkage. What is the formula? Loss is equal to shrinkage strain multiplied by Young's modulus of steel. Okay, I'll utilize the same formula. Therefore, loss is equal to shrinkage strain multiplied by ES. Okay, shrinkage strain is given as 0.0002 Young's modulus of steel. It is also given in the problem. How much it is given? 210 kilonewton per mm square. Correct? 210 kilonewton per mm square. So you convert that into Newton per mm square. 210 kilonewton per mm square. So if you convert into Newton per mm square, it is 210 into 10 power 3 Newton per mm square. Therefore, here you multiply 210 into 10 power 3. By this, you will get loss due to shrinkage. Loss is equal to, please calculate the answer. And the answer is, please cross check, 42 Newton per mm square. 42 Newton per mm square. Then loss due to shrinkage is over. Next you calculate loss due to creep. Creep coefficient is also given. C or third type of loss. Loss due to creep. Loss due to creep. Okay. So in the problem, the creep coefficient is given. It is given as 2.2. Okay. Creep coefficient is given as 2.2. Creep coefficient is equal to creep coefficient is equal to, it is given as 2.2. Okay. Now loss due to creep formula will be what? Loss due to creep is, loss due to creep formula is what? It is pi into FC into M. Creep coefficient is given. Okay, with respect to creep coefficient formula is pi into FC into M. Pi into FC into M. Okay, this is the formula. So where M is modular ratio, is it given? Please check in the problem. Modular ratio. Modular ratio it is not given, but ES and EC, Young's modulus of steel and concrete is given to 210 and 35. You can calculate the modular ratio. Modular ratio M. Modular ratio M is equal to ES by EC ESC is 210 divided by EC is 35. Okay, so you will get modular ratio as 6. Correct? Modular ratio as 6. Then pi is known, M is known, we need to calculate FC. What is FC? Stress in concrete at the level of steel. Okay, calculation of FC, you write. Again, you need to do some calculation for calculating this FC. So we have the formula for calculating the FC. What is the formula? FC is equal to P by A plus PE by I into E minus M by I into E. This is the formula. Okay. Now, whatever the cable we have, it is a parabolic cable. Okay. The FC is nothing but it is stress in concrete at the level of steel. FC is nothing but stress in concrete at the level of steel, but the level of steel is not constant with the length. Okay, it is varying with the length. Okay, level of steel is varying with the length. Therefore, what we have to do is we have to calculate FC at support and FC at the midspan. Okay, then we can calculate the average FC. Okay, first we will calculate FC at the support. Okay, FC at the support. Therefore, FC support is equal to at support. What is the eccentricity at the support? Eccentricity at the support is 0. Correct? Eccentricity at support is 0. At support, eccentricity is 0. Therefore, FC is equal to P by A plus. If you substitute 0 here, so you will get 0 minus 0. So FC is equal to P by A at support. So P is known. Okay, P is known. P is how much? Pre-stressing force is 250 in the cable. In the cable it is 250 kilonewton. Therefore P is 250 into 10 power 3. 250 into 10 power 3 divided by area of cross section is 45,000. Area of cross section, yes, it is 45,000 mm square. 45,000. Therefore, FC support is equal to, okay, this is support. Okay, it is 250 into 10 power 3 divided by 45,000. If you calculate, you will get 5.56 Newton per mm square. 5.56 Newton per mm square. Okay, now we got stress in concrete at the level of steel at the support. Similarly, you calculate at midspan. At midspan, eccentricity is how much? It is 250 mm. Okay, so you will have some value for eccentricity here, and moment of inertia is also required. That also you calculate. I is equal to, for rectangle it is BD cube by 12. Okay, BD cube by 12. It is 150 is the width, 300 is the depth, divided by 12 is equal to 337.5 into 10 power 6 mm4 is the moment of inertia. Okay, now at midspan, eccentricity is 250 mm. Moment of inertia is also known. Substitute in this, you will get stress in concrete at the level of steel at midspan. Therefore, FC midspan. Therefore, FC midspan is equal to P by A. P by A value is already known. It is 5.56. 5.56 plus PE by I. PE by I. Substitute now. P is 250 into 10 power 3 into E, eccentricity at the midspan is 250 mm, divided by I, moment of inertia 337.5 into 10 power 6 into E again into 250. into 250. Okay. Minus m by I into E. Minus m by I into E. Moment is required now. That you calculate now. That you calculate. Moment, total moment in the beam. Okay. So better you calculate total moment in the beam, then you can do this calculation. Okay. Moment I forgot to calculate. Okay. Dead load of the beam you calculate and live load you calculate total load, and for the total load you can calculate the moment. It's a very simple step. First you calculate the dead load of beam. How you calculate cross sectional area multiplied by density will give dead load. Cross sectional area you need to substitute in terms of meter square. Remember here, because density is in terms of kilometer per meter cube. So it is 45,000 mm square into 10 power minus 6. 45,000 into 10 power minus 6 meter square into density of the concrete is 24. So by this we'll get 1.08 kilonewton per meter. Okay, and live load on the beam is given. Live load on the beam is given. Okay, just go through the problem. Here you can see live load on the beam is given as 4 kilonewton per meter. Okay, it is 4 kilonewton per meter. Therefore, here live load on the beam, live load on the beam is equal to 4 kilonewton per meter. By this we'll get the total load. Therefore, total load W is equal to 5.08 kilonewton per meter. Now you can calculate the bending moment. Therefore, M is equal to WL square by 8. 5.08 into length of the beam is 10 square by 8. Okay. So you will get the answer as 63.5 kilonewton meter in terms of Newton millimeter. It is 63.5 into 10 power 3, sorry, 10 power 6 Newton millimeter. Okay. Now you can substitute everything in this equation. Fc is equal to P by A. Fc is equal to, therefore Fc is equal to P by A value is known, it is, I'll directly substitute 5.56 minus PE by I. 250 into 10 power 3 is the P, into eccentricity is 250 divided by moment of inertia 337.5 into 10 power 6 into E again 250 minus, okay, minus M by I into E. M is 63.5 into 10 power 6 divided by I is moment of inertia 337.5 into 10 power 6 into E again 250. So by this you'll get stress in concrete at the level of steel at midspan. Therefore, FC midspan, please calculate the answer. FC midspan is equal to, if you calculate the answer, you will get it as 4.81 Newton per mm square. Please check the answer. Okay. If you get any different answer, please tell me, we'll correct it. Okay. Now, at support, FC is 5.56, at midspan, FC is 4.81. Now you can calculate average stress. You can calculate the average stress. Write the diagram for the same. Say at support, the stress is 5.56. Okay, it is 5.56 at the support. Okay, and at midspan it is 4.81. At midspan it is 4.81. Okay, this is support. This is midspan. Okay, and similarly, if we calculate stress at other points and mark the points and join together, you will get a parabolic nature of the graph. Okay, you will get a parabolic nature of the graph. Okay, like this, you will get parabolic nature of the graph. Write properly. Like this. Okay. Now you need to calculate average stress. Okay, average stress. See, up to here it is known. Average stress is known. Okay, up to this point we have 4.81 as average stress. Okay, therefore average of C. Will you read? Therefore average FC is equal to 4.81. Okay, up to this point we have the average FC of 4.81. After this there is a parabola. Okay, this parabola you need to convert it into a rectangle. Okay, this parabola you need to convert it into a rectangle. Let me write one more diagram. Okay. Five 5.56. Now we will calculate this parabola, remaining parabola into rectangle. How to convert? It is 2/3 of this height. 2/3 of this height. Okay, this height is 5.56 minus 4.81. 5.56 minus 4.81. 2/3 of 5.56 minus 4.81 plus here height is 0. So at this point height is 0. At this point we have the height of 5.56 into 5.56 minus 4.81 plus 0. By this will get you this parabola is converted into average stress. Okay. Therefore the answer is 5.31 Newton per mm square. FC is equal to 5.31 Newton per mm square. I hope this calculation you all understood. See, up to here no problem, 4.81. Then what we have done, this parabola we have converted into equivalent rectangle. How to convert this into equivalent rectangle? 2/3 of average height on both sides. On the left side we have the height of 5.56 minus 4.81. On the right side we have the height of parabola as 0 at this point. With respect to this uh, red dotted line as baseline. Here height is 0. Here 5.56 minus 4.81. 2/3 of addition of those two heights on left and right will give it will convert it into a rectangle. So the average FC is now 5.31 Newton per mm square. Okay, average FC is now 5.31 Newton per mm square. Okay, now we can calculate loss due to creep. Okay, M is known, FC is known, pi is known. Just substitute. Therefore, loss is equal to therefore loss is equal to pi into that is 2.2 into FC 5.31 into M is 6. Okay, therefore it is 70.092 Newton per mm square. So this we got loss due to creep. Okay, if there are any doubts in this calculation, you can ask students. Now the next type of loss remaining is fourth one, loss due to relaxation of steel. Loss due to relaxation of steel. Okay, it is a very simple calculation. It is calculated as a percentage of initial stress. Okay, it is directly given. It is how much given? For 4% it is given in the problem. Relaxation of stress in steel 4%. Okay, therefore loss is equal to percentage of initial stress. Initial stress. It is calculated as loss due to relaxation is calculated as in percentage of initial stress. Okay. Students, I'll be back in a minute. Please keep solving. It is given as 4%, correct? It is given as 4%. Relaxation of stress, percentage of relaxation of steel is given as 4%. Therefore, initial pre-stress is known. Okay, it is 500 Newton per mm square in the cable initial pre-stress. Therefore, loss is 4%. That is 4 by 100 of 500. Therefore, loss is equal to 4% of 500 means 20 Newton per mm square. Okay, 20 Newton per mm square. Okay, to this loss due to relaxation is over. Next is last one. This one loss due to anchorage slip. Loss due to anchorage slip. Correct. So what is the formula for loss due to anchorage slip? So delta by L into ES. Loss is equal to delta by L into ES, and this delta is given, slip value is given, amount of slip. Delta, it is given as anchor slip at jacking it is given as 3 mm. Okay, delta is equal to 3 mm, and length of the beam is 10 meter, 10,000 mm, and ES is also known. Therefore, loss is equal to 3 by 10 meter means 10 into 10 power 3 millimeter into 210 into 10 power 3 Newton per mm square. Okay, please calculate the answer. Therefore, the loss is equal to 63 Newton per mm square. Okay. Now we have calculated all the loss. Okay. Only one type of loss we have not calculated, that is loss due to elastic shortening. Okay. This is the post tensioned beam. In case of post tensioned beam, loss due to elastic shortening will be there if the cables are pulled one by one. Okay. Here it is only one cable and it is pulled simultaneously. There is no loss due to elastic shrinkage. Therefore, the total loss is equal to. Therefore, the total loss is equal to sum of loss due to friction 81.4 plus 42 plus 5.56 plus 5.56 sorry for not 5.31, sorry, it is FC. No, loss due to creep is 70.092 and 63 70.092 plus 20 plus 20 plus 63. Yeah. Therefore, the total loss, if you calculate, you will get 276.49 276.49 Newton per mm square. Okay, so we can also calculate the percentage of loss. Therefore, percentage loss is equal to total loss 276 out of 500 initial stress into 100. So it is 55.3%. So to this, the problem is over. If you have got any doubts, we can ask students. Any doubts in the calculation at any step, please ask before moving on to the next problem. Okay, thank you. So please write down the next problem. A post tension concrete beam. It is also a problem on a post tension concrete beam. All of you write the problem quickly. A post tension concrete beam, 100 mm wide, 300 mm deep. Meanwhile, I'll write the diagram. Please go through the question. A post tension concrete beam 100 mm wide by 300 mm deep. Write the cross section. Hundred mm wide, 300 mm deep. Okay. Spanning over 10 meter, length of the beam is given as 10 meter. Length of the beam is 10 meter. Spanning over 10 meter. Is stressed by successive tensioning and anchoring of 3 cables 1, 2 and 3 respectively. Okay. The cross-sectional area of each cable is given as 200 mm square. Below I will write that. Cross-sectional area of each cable is given. There are 3 cables and they are stretched successively. Cross-sectional area of each cable is given as 200 mm square. 200 mm square. And the initial stress in the cable is 1200 Newton per mm square. Initial stress in the cable is given. That is initial pre-stress. Is given as 1200 Newton per mm square. And modular ratio is also given. It is given as 6. M is equal to 6. Okay. Next, very important, you go through it. The first cable is parabolic with the eccentricity of 50 mm below the central axis at the center of the span and 50 mm above the central axis at support section. First, you write the neutral axis or the central axis for the figure. Okay, just to see, he has clearly told the profile of the first cable. Okay, the first cable is parabolic with eccentricity of 50 mm below the central axis at the center of the span. So at the center it is 50 mm eccentricity. Okay. And 50 mm above the central axis at the support. Okay. Cable is having 50 mm. So this is the cable of the first profile of the first cable. Okay, I'll go through once again. First cable is parabolic with eccentricity of 50 mm below the central axis at the center of the span. Okay, at the center 50 mm eccentricity and 50 mm above central axis at the support. Here I mentioned. So I'll write the diagram now. Cable, first cable profile. So this is the first cable profile. Okay, here also it is having 50 mm at the support, 50 mm at the center. Here also 50. Okay, I hope you understood this. Then just read the cable profile of the second cable. Profile of the second cable. The second cable is parabolic with zero eccentricity at the support. Zero eccentricity at the support and at an eccentricity of 50 mm at the center span. At the center it is 50 mm only. Now I'll write the diagram of the second cable. Zero at the support and 50 mm at the center. This is the profile of the second cable. Then third cable profile. The third cable is straight with uniform eccentricity of 50 mm below the central axis. Okay. The third cable is a straight cable. It's a straight cable. Okay. With the constant eccentricity of 50 mm throughout the length. Okay. This is what the cable profile given. Okay. Therefore, for cable 1, okay, for cable 1, eccentricity, for cable 1, eccentricity, I will call it as E1 is 50 mm. Okay. And one more important thing, students, here eccentricity below the central axis is represented by positive sign and eccentricity above the central axis is negative, represented by negative sign. So here cable 1 is having eccentricity above the central axis, above the neutral axis at the support. So it is minus 50. Minus 50. Okay. Then E2. Okay. This is for cable 1. Okay. For cable 2, E2. Eccentricity at the support, it is 0. There is no eccentricity. Similarly, for cable 3, eccentricity at the support E3 is how much? It is plus 50 below the axis 50 mm. Okay. Similarly, at center of the span, all the cables, cable 1, 2, 3 are having same eccentricity, that is 50 mm. That is here I will write it as E1 is equal to E2 is equal to E3 is equal to 50 mm. Okay. Now, moving on to the question. Estimate the percentage loss of stress in each cable if they are successively tensioned and anchored. Okay. The question is we have to estimate the percentage loss of stress in each cable if they are successively tensioned and anchored. Okay. Now, you calculate initially pre-stressing force, you calculate pre-stressing force. Pre-stressing force is equal to what? Stress into area. Stress in the cable is given. Stress into area of cable area of cable. Stress in the cable is 1200. Area of cable is given as 200. Therefore, the answer you get is 240,000 Newton. Okay, or else 240 kilonewton. Okay, and area of cross section also you can calculate. It is 100 by 300, and area of cross section, area of cross section A is equal to 100 by 300, that is 30,000 mm square. Okay. Okay, these are all the basic parameters that are required for the further calculation. Okay, prestressing force, area of cross section. Then you also calculate moment of inertia. Moment of inertia I is equal to PdQ by 12. P is 100, D is 300, Q by 12. It is 225 into 10 power 6 mm4. Okay, 225 into 10 power 6 mm4. Okay, these are all the basic parameters required for the further calculation. Now, what is the question? Estimate percentage of loss of stress in each of the cables if they are successfully tensioned and anchored. So the question is, when cable 1 is stretched and anchored, what is the loss in the cable 1? That is the question. And when cable 2 is stretched and anchored, what will be the loss in the cable 2? When cable 3 is stretched and anchored, what will be the loss in cable 3, 2 and 1? Like this. Okay, you need to calculate. Now we'll go one by one. We'll go one by one. When A when cable 1 is pulled and anchored, what will be the loss in the cable 1? Loss in cable 1 will be how much? It will be 0. Loss due to elastic shorting, students. Okay. The basic principle says that if a cable is stretched simultaneously, then there will not be loss. So as this is the first cable, okay, first cable there, and it is stretched and released, there is no loss in the cable 1. When cable 1 is stretched and anchored, there is no loss. Okay. Then second one, when cable 2 is pulled and anchored and cable 2 is pulled and anchored. Now we have to calculate loss of stress in cable 2 and loss of stress in cable 1, because when after the cable 1, cable 2 is stretched and anchored, so due to the stretching in cable 2, there will be loss in cable 1. Okay, so the loss in cable 1, loss in cable 2 will be 0, but there will be loss in cable 1. Loss in cable 1 will be equal to M into FC. M into FC. Okay, this is loss due to elastic shafting formula. M into FC. Okay, students. When cable 2 is stretched and anchored, already there will be existence of the cable 1. Because of pulling and releasing of cable 2, there will be effect in cable 1. There will be loss of stress in cable 1. Okay, that is calculated M into FC. Okay, and we have the formula for calculation of FC. FC is equal to P by A plus PE by I into E minus M by I into E. Minus M by I into E. And here the live load on the beam is not given in the problem. Okay, live load on the beam is not given. So as the live load is not given, there will not be any live load moment. We'll ignore this. Okay, and we will ignore dead load moment also. Here we can write a note. Live load is not given, and neglect dead load. Okay, and very important thing here, when cable 2 is stretched and anchored, if you are calculating loss in cable 1, okay, so here this becomes PE2 and PE1, means loss due to cable 1 due to stretching of cable 2. This is the meaning. Okay, so E1 and E2. So in the previous case, I used to write PE by I into E. No, this is what the reason. Okay, this is what the reason. So when cable are stretched individually, okay, one after the other. So in this way we need to denote. Okay, so here E2 represents E2 E1 represents loss in cable 1 due to stretching of cable 2. That is the meaning. Okay, here below you can write where E2 is equal to eccentricity of cable 2 and E1 is equal to eccentricity of cable 1. Okay, again it is a parabolic cable. Okay, parabolic cable at support and at midspan you need to calculate FC support. FC support is equal to, and E2 is equal to FC support. Before that you write at support okay, at support we can say at the support E2 is equal to 0 and E1 is equal to minus 50. I'll write the right here. E1 is equal to minus 50 mm and E2 is equal to 0. Refer figure. Okay, therefore FC support is equal to P by I, P by A. P resisting force we have calculated. How much it is? 240 kilonewton or 240,000 Newton. 240,000 divided by cross sectional area A also we have calculated 30,000. Okay, P by A plus P by I into E, or P by I into E. PE is 240,000 into E. E2 is how much? 0. PE2 divided by I is moment of inertia. How much we got? 225 into 10 power 6. 225 into 10 power 6 into E1 is minus 50. Okay, here is minus 50. So this here 0 is multiplied, this whole term becomes 0. Therefore, F support is equal to calculate it, and it will be 8 Newton per mm square. Okay, similarly at midspan, okay, at midspan the eccentricity is same for all the cables. E1, E2, E3 is equal to 50 mm. E1 is equal to E2 is equal to 50 mm. Therefore, FC midspan is equal to same 240,000 divided by 30,000 plus 240,000 PE2 50 divided by 225 into 10 power 6 into 50 into 50. That's it. Next term is 0. So you will get FC midspan is equal to 10.67 Newton per mm square. Okay. Now you can calculate the average FC. At support it is 8 and at midspan it is 10.67. 8 and 10.67. Here it is 8. Okay. Now if you want to calculate average stress, same as previous problem. So average FC is equal to, therefore average FC is equal to 8 plus this length is 10.67 minus 8. Correct? The full length is 10.67. So 8 plus 10.67 minus 8, 2/3 of 10.67 minus 8. Okay. So in the next coming calculation, friends, I will be directly writing the this calculation. I will not write the diagram. 9.78 Newton per mm square. Okay, and m is equal to given as 6. Therefore loss in cable 1 is equal to m into FC. M is given as 6, FC is 9.78. The answer is 58.68 Newton per mm square. Okay, which means that when cable 2 is pulled and anchored, loss in cable 2 is 0 and loss in cable 1 is 58.68 Newton per mm square. Similarly, we have to do the calculation for cable 3. Third one. See, when cable 3 is pulled and anchored, when cable 3 is pulled and anchored, you need to calculate loss in cable 3, loss in cable 2 and loss in cable 1. Okay. So when cable 1 is pulled and anchored, loss in cable 1 is 0. When cable 2 is pulled and anchored, loss in cable 2 is 0 and you have calculated loss in cable 1. Similarly, when cable 3 is pulled and anchored, loss in cable 3 is 0. Loss in cable 3 is 0 and loss in cable 2 and loss in cable 1 you need to calculate. Okay. First one is over. Second one, loss in cable 2. Cable 2 is equal to m into FC. Okay, where FC is equal to P by A plus PE by I into E. Okay, and this third term is 0 because moment is 0. Now, with respect to notations of E, you are calculating loss in cable 2 with respect to when cable 3 is pulled and anchored. Okay, you are calculating loss in cable 2 when cable 3 is pulled and anchored. So you need to substitute E3 and E2 here. And at support, just look into the values of E2 and E3. What is the value of E2 at support? From the figure, E2 at support is 0 and E3 at support is plus 50. E2 is 0 and E3 becomes plus 50 mm. Therefore, FC is equal to P by A. Okay, where P is 240,000. 240,000 divided by area is 30,000. 30,000, or else you can directly substitute the value of P by 8. It is 8. No, we got it as 8. We can directly substitute it as 8 plus 240,000 into E3 is 50 divided by 225 into 10 power 6 into 0. So this whole term becomes 0. Correct? So FC is equal to FC support. FC support is equal to again 8 Newton per mm square. Okay, this is loss in cable 2 when cable 3 is stretched and anchored, pulled and anchored. Okay, and at midspan, all the values are constant only. E1 is equal to E2 is equal to E3 is equal to 50 mm. Okay, therefore FC is equal to 8 plus PE3 by I into E2. P is 240,000 into E3 is 50 divided by I is 225 into 10 power 6 into E2 50. Both are plus. Okay. If you calculate FC, you will get as 10.67 Newton per mm square. That is at midspan. FC midspan. Okay, 10.67. Therefore, average FC. Therefore, average FC is equal to. I'll directly write the calculation now. It is minimum value is how much? Minimum is 8 plus. Sorry, difference between the two. Minimum value plus 2/3 of difference between larger value and the smaller value. 10.67 minus 8. Okay. In this way, you can directly calculate the average FC. It is 9.78 Newton per mm square. Okay. Now, when cable 3 is pulled, loss in cable 2. Therefore, loss in cable 2. Loss in cable 2 is equal to M into FC. 6 into FC is 9.78. So we will get 58.68 Newton per mm square. 58.68 Newton per mm square. Okay. Now what you have calculated? When cable 3 is pulled, cable loss in cable 3 is 0. Loss in cable 2 is 58.68 Newton per mm square. Similarly, you need to calculate loss in cable 1 now. Third one. Loss in cable 1. Loss in cable 1. Okay. So at support, before that you write the formula. FC is equal to P by A plus PE by I into E, and the third term is 0. Okay, now what you are doing? You are calculating loss in cable 1 when cable 3 is pulled and anchored. So E3 and E1 you need to substitute. Okay, therefore at support E1 is equal to how much? Minus 50, correct now? E1 is equal to minus 50 and E3 is equal to plus 50. E1 is equal to minus 50 mm. E3 is equal to plus 50 mm. Therefore, FC support is equal to P by A value is 8 plus P 240,000 divided by 225 into 10 power 6 into E3 is 50 into E1 is minus 50. So by this you will get the answer as 5.33 Newton per mm square. 5.33 Newton per mm square. Similarly, at midspan, both E1 is equal to E3 is equal to, you will get 50 mm only. You have 50 mm only. Therefore, FC midspan is equal to 8 plus 240,000 divided by 225 into 10 power 6 into 50 into 50. So answer is 53 point, 58 point, 10.67. If you calculate this, you'll get as 10.67 Newton per mm square. If we can calculate this answer. Yes, 10.67 Newton per mm square at midspan. Okay, therefore average FC will be equal to, therefore average FC will be equal to smaller value plus 2/3 of larger minus smaller, 10.67 minus 5.33. Okay, by this we'll get average FC, that is 8.89 Newton per mm square. 8.89 Newton per mm square. Okay, therefore loss in cable 1 is equal to M into FC is equal to M modular ratio is 6, FC is 8.89. Okay, so it is 53.34 Newton per mm square. Okay, I hope you understood the procedure, students. So when the cables are pulled and anchored successively, see when cable 1 is pulled and anchored, loss in cable 1 is 0. When cable 2 is pulled and anchored, loss in cable 2 is 0, and you have calculated loss in cable 1. When cable 3 is pulled and anchored, you have loss in cable 3 is 0, and you have calculated loss in cable 2 and loss in cable 1. Okay. Now, finally, you need to calculate loss in each cable, total loss in each cable. Total loss in each cable. Below, right? Finally, loss in each cable. See for cable 1, total loss will be, see for cable 1, when cable 1 is pulled and anchored, loss in cable 1 is 0. When cable 2 is pulled and anchored, loss in cable 1 is 10.67. Sorry, loss in cable 1 is 58.68. 58.0 plus 58.68. And similarly, when cable 3 is pulled and anchored, loss in cable 1 is 53.34 plus 53.34. So it will be 112.02 Newton per mm square. Then similarly we have to calculate cable 2, total loss in cable 2. See when cable 1 is pulled and anchored, there is no existence of the cable 2 only. Okay, there is no loss only. When cable 2 is pulled and anchored, loss in cable 2 is 0, 0 plus 0 plus. When cable 3 is pulled and anchored, loss in cable 2 we have calculated here. We have got it as 58.68 plus 58.68. So you will get 58.68 Newton per mm square. Then similarly for cable 3, So when cable 1 is pulled and anchored, there is no loss in cable 3. There is no existence of the cable 3 only. Similarly, when cable 2 is pulled and anchored, there will not be any existence of the cable 3 only. There is no loss. Similarly, when cable 3 is pulled and anchored, loss in cable 3 is 0. Therefore, loss in cable 3 is 0. So knowing the total losses in each and every cable, finally the average loss you can calculate, that is 112.02 plus 58.68 plus 0 whole divided by 3. If you calculate, you will get it as 56.9 Newton per mm square as average loss. Okay. And you can also calculate percentage loss in each cable. Percentage loss in each cable. Each cable will be equal to, for cable 1, total loss is 112.02, 112.02 Newton per meter square. Out of initial stress is how much? It is given in the problem. Initial stress is given as 1200 divided by 1200 into 100. 1200 into 100. So it is 9.34%. Similarly, for cable 2, total loss is 58.68 divided by out of 1200 into 100. So percentage loss will be 4.89%. And cable 3. So it is having 0 loss, so 0%. So 0%. Okay. Okay, students, let's do this. This problem is over. If you have got any doubts at any point of calculation, you are free to ask. Any doubts in this particular problem? Okay, thank you. Please write the next problem. Problem number 6. Problem number 6, you write. A simply supported beam of span 9 meter. Write the problem quickly. Take 2 minutes time. Hey, yaar, Meanwhile, I'll write the diagram. What is the question? A simply supported beam of span 9 meter is processed with a parabolic cable which has maximum eccentricity of 200 mm at midspan and 35 mm at the support. Okay, at support eccentricity is 35 and at midspan it is having 200 mm eccentricity. Okay, at midspan eccentricity is 200. Okay, at support 35 mm is the eccentricity. Okay. The beam is 250 by 300 mm in section. Cross section is given 250 by 300. So 50 by 300. Okay. Area of steel in the cable is given. Okay. Area of steel is 700 mm square. 700 mm square. Initial pre-stress is given. Initial pre-stress 1000 Newton per mm square. Newton per mm square. Anchorage slip delta is given. Delta is equal to 2 Nm. Anchorage slip. Creep coefficient is given. Shrinkage strain in concrete is given. And oval constant, coefficient of friction, relaxation of stress in steel, modular ratio, everything is given. Required for the calculation. All the constants are given. Okay. We just go through the question. The wires have to be tensioned 2 at a time from one end to a value of F1. Okay. To a value of F1 so as to overcome frictional resistance and then relax to a value of F2 so that immediately after anchorage an initial stress of 1000 Newton per mm square would be obtained at the jagged end and jagged ends. Okay, hence determine final design stress available in tensioned steel. Okay, and Young's modulus of steel is also given. Okay, what happened? What he said is in this problem, there is relaxation given in the induced stress in the steel with respect to loss due to friction and loss due to anchorage. Okay, which means that the initial stresses are applied by considering this loss due to friction and the loss due to anchorage. That is the meaning here. That is the meaning. Okay. So as to overcome frictional resistance. Overcome frictional resistance means the loss due to friction should be reduced. Okay. It should be reduced. Means it should be zero. To make loss due to friction zero, what will be done is initially while applying the stress only, this additional friction loss due to friction loss due to anchorage slip will be added to the actual stress and it is applied. Then this loss due to friction and anchorage will be overcome. Okay. So this is what the problem given. So to make the relaxation of stress due to loss due to friction and the loss due to anchorage, what should be the initial stress applied? That is the first question. That is the question here. Okay. I hope you understood the question. So in the next class, we will solve this. To this, we will end the class. Thank you.